Hey everyone, welcome back, and let's write some more Leetcode today. Very interesting problem today. Count number of maximum bitwise OR subsets. And I'm actually going to show you 4 solutions to this problem, and each of them is actually going to pass on Leetcode. So this is going to be a big boy video, and you know what that means. By the end of this video, you will yourself be a big boy or girl. And I'm also going to briefly explain to you why the Leetcode editorial for this problem, and honestly the Leetcode editorials in general, are just so bad. I really just don't like them. Let's get into it. The idea is we're given an input array nums. We can break this list into subsets. Remember what the word subset means. It's not a contiguous subarray. It's actually more general than that. It's basically like a subsequence. So for example, for every number, we can choose to include it or skip it, and we can kind of do that recursively. So next we'd pick 2 or skip 2. And so each of these paths would count as a subset, and like the path has to go down to a leaf node in this recursive tree. And it's possible that we do end up with like an empty subset, but in this problem, we want to ignore the empty subset, but I'm going to tell you why we're actually never going to end up with an empty subset, or at least not one that we would count. Now, among these subsets, for these numbers, we don't want to add them up. We want to do something different. We want to bitwise OR them together. So just to briefly remind you, if you have a number like this, 1, 1, and if you have a number like this, which is 5, so this is 3 XORed with 5, you bitwise XOR them, or sorry, not XOR, bitwise OR them. The symbol for that is this. So if you bitwise OR them, you just look at the 2 spots. If they're the same, or if one of them is set to a 1, you get a 1 in the output. So here we get a 1, here we get a 1 as well, here we get a 1 as well, and the rest would be zeros because they are zeros in all positions. So what does this OR property tell you? Well, when you OR 2 numbers together, the result is never going to be smaller than either of the values. Because remember, if you take a number like this and you OR it with just 0, you're going to end up with that number itself. It's never going to get smaller than that. If you OR it with a different number, maybe it'll stay the same, but it'll never get smaller, and it could get bigger. So that's very important to know about OR. In that sense, it's kind of similar to addition. Now, to finally get into what the problem is asking of us, among all possible subsets of this, we want to find the max bitwise OR, the maximum. So first of all, how exactly could we do that? Well, we could go through every single possible subset and then among those compute the max, but actually the max is more simple to get than that because of what I just told you. We can just scan through the input and OR all of these values together. So kind of like running like a reduce operation on these where the operation is OR. And then the fact that we have that is good, but it doesn't remove the need to still do that recursion, because we now want to count the number of different subsets that have the same bitwise OR as the max bitwise OR. And when we say different subsets, imagine that we had duplicates in this. Like suppose we have 2 3s. This is one subset, and this is a different subset. They count as different subsets, even though they make up the same values. Like both of them have 3 and 5 as the subset, but they have distinct elements. Like this is a different element than this one, so it counts as a different subset. Okay, now let's get into the first recursive solution. Conceptually, it's pretty simple. Go through the input and just create every possible subset and then OR those numbers. So we have 3 or we skip it. Here we can choose 2 or we skip it. Here we can choose 2 or skip it, etc., etc. So I'll just kind of do one of these real quick. Here we can get 1 or skip it. Here we could get 5 and skip it. So as we're computing this path, we could have 2 variables. One is index I. It's going to tell us which position we're currently at. And another could be the current OR that we have. Initially, it'll start as 0. Every time we choose an element, we're going to take that element and OR it with the current OR. So by the time we reach the bottom, that's the base case, we're going to have something. We're going to have 2 ORed with 1 ORed with 5. This is what we're going to have. We can compare it to whatever max OR that we computed earlier, and then If these are equal, we increment the result by 1. If they're not, we don't increment the result by 1. You actually didn't necessarily need to compute this up front. You actually could recursively solve this just by constantly updating whatever the max OR is. If you ever came across a current OR that's greater than the max, you could update that and then reset the count. If we are counting it in a result variable, we could always reset the count to 0 every time we update that, but it's better to just compute this up front. This is the solution I'm going to show you. In terms of time complexity, it's going to be 2 to the power of n because of this decision tree. The space complexity is going to be linear because of the height of this decision tree. So before we get into the recursion, let's compute the max OR. I'll initialize it to 0. We'll go through every number in the input and then OR it with the max OR just like that. And then I'm going to do my DFS. Now, we're going to do it this way where we have the index I and we have the current OR. I'm not going to pass in the max OR as a variable because it's already accessible, or it will be accessible the way I do it. We could do it a couple different ways where we could have a variable out here, which is called result. And then down here, we could return that result. That's actually a very valid way of solving this problem this way. I'm actually going to do it slightly differently. I'm going to have this function return the sum of all of those. I'll code it both ways for you actually, but the reason I prefer the second approach is because then it's more easy to just add memoization to that solution, which is what we're going to be doing in a bit. So let's start doing it this way. We have our result. I'm going to be accessing these two variables and they're primitives, so we actually need to declare them as non-local if we want to access them. So that's what I'm going to do here, max OR, and then I'm going to do my base case first. What's the base case? We reach the leaf node, which means we reach the end of the input nums. And then what am I going to do? Well, I'm going to return for sure, but before I return, I want to potentially update the result. I only want to increment it by 1 if the current OR is equal to the max OR. If it's not, then I can just increment it by 0, which is not going to change it. So this is how a ternary operator works in Python. Next, I'm going to do my recursive call. There's two cases. We either skip I or we include I. I'm going to start with the skip case because then we don't need to do any cleanup afterwards. So this is what I'm going to do. DFS, move to the next position, and the current OR is going to remain unchanged because we're skipping the current element, so we don't need to do anything. The current OR stays the same. If we include the current element in our current OR, then we're going to do the same thing here. DFS, move to the next position, but update the current OR to be this now. Current OR is going to be ORed with the element at index I. There we go. From here, we don't need to return anything because we're updating the result out there, but we do need to remember to actually call the DFS. That's something I often forget. So out here, let's call DFS starting from position 0, and the current OR is going to start at 0 as well. So this is the whole code. Let's run it. You can see here, it works. It's pretty efficient. Honestly, in terms of time complexity, this is about as efficient as you can get. I'll talk about why, but I want to update this solution so that instead of updating the variable out here, we actually return it. So I'm going to get rid of this return statement here. I'm going to return the result of DFS. And within the function, first, I'm going to get rid of the result variable out here. And I'm going to not declare it non-local. And down here, if we reach the base case, we can return 1 or 0, depending on this condition. So instead of adding this to the result, we're just going to return it from the function itself. And then out here, these two recursive calls, each of them is now returning a value. It could be 1 or 0, or it could be bigger than that, but it can only be bigger than that if we actually return the sum of these two values. So that's what I'm going to do here. I'm going to do that and then add this. I'm going to get rid of these comments. And here, I'm going to wrap that in a parenthesis. So now we're just taking the sum of these two and returning that. So pretty much the same solution. You can see here that this one also works. Now, to go back to the drawing board for a second, we can, generally speaking, take recursive solutions like this and add memoization to them. But it depends on the constraints of the problem, whether that memoization is actually going to be useful or not. So let's see what would happen to the time complexity if we added memoization, and let's then determine, given the constraints of the problem, if that's actually useful or not. So how would we add memoization? Remember, there's two parameters we're keeping track of, index I and the current XOR, or current OR. I'm really sorry about making that mistake a lot. And so the number of different combinations of these two variables is going to determine the subproblem. For example, like when we get down here, the subproblem is we're at index I equals 1 and the current OR is equal to 2. When we get down here, we're at subproblem I equals 1, or sorry, I equals 2, and the current OR, I believe 2 and 1 ORed together, I think that's going to be 3. So the current OR would be 3. Now it's possible that there's another path somewhere where we skip a bunch of elements and then we have 3. And suppose like somehow we're also at the same index. Maybe like here we go down here, we skip an element. So here we're at I equals 2, and then the current OR is still equal to 3. And then maybe the third element here was actually a 3. Maybe we took a path from here where we skipped all of these and then we only ended up with a 3. So basically what I'm saying is we are going to sometimes see the subproblem repeat, in which case we can throw that into a cache. So the size of the cache is going to be 2 dimensions. I can be from 0 through n, where n is the length of the input. I believe it's actually n minus 1, but roughly n. So the space complexity needed for that cache is going to be O of n multiplied by how many different possible XORs could we possibly have? Well, an easy way to approximate that is just to take the max possible OR that we could have. So let's leave it at that. Whatever the max OR is, that's pretty easy for us to just compute. But what could it actually be? Because now this is the space complexity, and this is actually also the time complexity, because this is how many distinct subproblems we're going to have. If we see a subproblem repeat, we can immediately return, and then it's going to be constant time. So what exactly is the time complexity now? Before we had 2 to the power of n. Is this better or worse? Well, n is relatively small in this problem. It's 16. What's the max possible OR that we could have? Well, in this example, given that the max number could be 10,000, it's going to be something like this. In binary form, I'm not exactly sure what that would look like, but the max OR among those values can't possibly be bigger than 2 times the max. So this equation, 2 times max is less than or equal to the max OR, and max means the max element in the input. Why is that the case? Well, imagine if the max number in the input had binary representation of something like this, meaning that this is the most significant bit. And if no other element has a significant bit that's set higher than this one, of course, none of the other elements are going to be greater than this one. So that's kind of the definition of the max element. So we can assume that to be true. Therefore, the best we could do to this element is set all of these bits, turn all of them into 1. So all of them would be set. If we do that, we practically doubled that number. We didn't do anything more than that, because this is 2 to the power of 0, this is 2 to the power of 1, etc., etc. When we take all of these, this is always going to be 2 times all of those combined, roughly speaking. Basically, we can say that the max in this case is going to be n, which is up to 16 times 10,000 in this case. Now, what does that number become? It becomes 160,000. Isn't that right? Well, what was the solution we had earlier? 2 to the power of n. Well, that was 2 to the power of 16 in the worst case. And that number is roughly 65,000. So actually, given the constraints of this problem, the original solution we had was better. Now, I'm still going to code this one up for you, but I think this sort of analysis is important because it kind of shows you that memoization, adding it to a backtracking solution, most of the time, it's not useful. I mean, why would the constraints actually be this small? Why are we dealing with such small numbers? Usually, that's not going to be the case. So theoretically, when would a solution like this, like down here, actually be better than the solution up here? Only when n is very, very large, which could happen. And like the size of the input could technically be 1,000. So in that case, the memoization would definitely be useful, but in this example, it's not. I also just recognized that I have 10 to the power of 5 when technically we should have doubled this. So that would have been 20,000. So this would have been 320,000, but minor detail. So let's code this one up now. So not a lot of changes that we need to make in this case. Just need to add caching to this. So instead of having a hash map for the cache, I'm actually just going to have a 2-dimensional grid because we know the size of the grid. I'm going to have a row for the max OR, like whatever the current OR could possibly be. is bounded by this variable that we already computed. So I'm going to set this to -1 as like a default value, and the size of this array is going to be max OR. But I'm actually going to add a +1 to this because the ORs that we are computing, none of them are possibly going to be 0 because every number in the input is greater than or equal to 1. So the max OR is never going to be 0 and the current OR is never going to be 0. So the number of slots that we're going to need for this is going to be +1 because we're going to ignore the 0 slot, the index 0. And so this is one row, and we need this many rows for however many positions we have in the input. So I'm going to do list comprehension in Python. So for in range length of nums, just like this. If you're not familiar with list comprehension, you can probably check out my Python for Coding Interviews course. But now that we have that, we need to add a base case in this function for that. So I'm going to say if we've already computed the value here for the ith row and value current OR, this subproblem, if we've already computed the result of this subproblem, we know that if the count is not -1. So here I'm going to say if this is not equal to -1, I'm going to return whatever we ended up caching in here. I'm sorry about my bad spelling. So we're almost done now. We just need to actually set this. So instead of just immediately returning the result, we're going to cache the result before we actually return it. So I'll make a bit more space here. And then down here, we will return that same result. This is, I believe, the entire code. Let's give it a run. And you can see that this one works as well. It's definitely not as space efficient though. So keep in mind that the previous solution was O of n space. This one is not O of n space. This one is O of n times the max OR, because that is the dimensions of this. And the max OR is roughly equal to the max element in the input. So now let's try to take this recursive solution and try our best to translate it into a bottom-up solution and see if there are any optimizations or any improvements that come from that solution. It's going to be kind of difficult because subsets are naturally computed in a recursive fashion. So doing them bottom up is somewhat unintuitive, but once I show you how to do it, it's actually not that bad. So first of all, we start with 0 subsets. In other words, we have like the empty subset. And then we want to get all subsets that have 3 in them. So we can kind of go through this and then we'll end up with this. So now these are all the subsets that we have. Next, we're going to take 2 and we're going to go through all of these subsets and add 2 to them. So now we're going to end up with something like this. We add 2 to the empty subset and we add 2 to the subset with just 3. So these are all possible subsets we can have with these 2 elements. You probably see where I'm going with this. Now we're going to take 1 and add them to all of these subsets. We're going to leave these subsets as is, but we're going to create 4 new subsets, each with 1 added to them. So we're going to get 1 here, we're going to get 1, 2 here, we're going to get 3, 1 here, we're going to get 3, 2, 1 here. Now I'm going to stop it here. So you probably get the idea of how we're going to add subsets to this. We're going to have, let's say, like a list of subsets, and then we're going to iterate over them like with a nested loop. We're going to iterate over all these elements, and then at the same time, we're going to iterate over our current list of subsets, but we're not actually creating subsets, right? So how exactly are we going to solve this bottom-up dynamic program? We're trying to count the number of subsets with the max OR value. And in order for us to do that, we have to solve the subproblems where we count subsets with smaller OR values. So what would that grid look like? Because that's what bottom-up dynamic programming is about. It's either a one-dimensional array or it's a two-dimensional grid, and sometimes it can be even more dimensions than that. On the left, it's going to be my I pointer. It's going to tell me which position I'm at. So I'll have 0, 1, 2, 3. And up here, I'll have my XOR values, all possible XOR values. So that's kind of tricky. What's the range of that going to be? Well, it's going to be from 0 all the way up until our max XOR. So I think in this example, it looks like it is 7. So that's good enough for us. And I'm not going to fill in this entire grid. I'm just going to try to give you like an idea of how we're doing this. So this first row would be all possible subsets that we can get with the element at index 0, which is 3. So we can only get this subset, like that's the OR of the subset, it's 1. And the rest of these are going to be 0, except for this one over here, because we technically do start with an empty subset. So that's also going to be 1, and then these are going to be 0. this is kind of like our base case. So now when we compute all possible subsets that we can get from these elements, I'm going to take this one, and then I'm going to iterate over all of these. I'm going to see that this one has a 1, so that means that there's a subset, and the OR of that subset is 0. So now I'm going to take this number 1, OR it with that, and of course, I'm going to get 1 in the output. So that tells me that this is where we want to add the count to. So I want to set this to 1. I want to add 1 to the count. Then I'm going to continue scanning through this. These are 0, so we don't do anything with them. But I'm going to see, okay, now I have 1 subset with an OR of 3. So I'm going to take 1, OR it with 3. And the result of that, I believe, is, I think it's just 3 still. So just to be sure, 1 ORed with 3. Yep, that's 3. So what should I do? Should I put a 1 over here? Because then we'd end up with something like this. Remember what this row is supposed to represent? It's supposed to represent the counts of the ORs. Like these are the OR values, and these are the counts if we had these two elements to choose from. So in reality, we actually want to take this whole row and add it with this whole row. So the easiest way to do that is just to start with this row in the first place. So instead of initializing this thing to all zeros, I want to just copy that to this initially, and then I want to take these values and add them to that. So actually this row is going to end up looking like this: 1, 1, 0, 2. Because we have 2 possible ways that we could get an OR of 3. And so then we just continue to fill this in. Now, this is a valid way to solve this problem. In terms of time and space complexity, I believe it's going to be the same because we're filling it in n times the max OR. So it's the same in terms of time and also in terms of space, but we can optimize this because, as you notice, when we're computing a given row, we're only going to look at the values in the previous row. So we can actually optimize the space to be O of the size of this row, which is going to be the max value. And we can also make one more optimization. Do you notice how like the max value is probably going to be really, really big? And a lot of these zeros are kind of useless. We don't actually have to visit most of them. We only care about the values that are actually set. So rather than using a grid, this is one of the few instances where it's actually more efficient to use a hash map for our cache rather than a grid. Because yeah, hash maps have collisions, but at least we're going to skip all of these empty spots. I mean, what's the point of iterating over all of them every single time? In the worst case, our time complexity still is going to be the same. It's still going to be n times the max element, but in most cases, we're not actually going to iterate over the entire thing. So in my case, each of these rows is going to be a hash map where we're going to map the max value to the count of that max value. So for example, like this would look like this in our hash map. Here, the key is going to be the max value. So I have 0, I have 3. I'm going to map 0 to 1. I'm going to map 3 to 1. And all the other ones aren't going to exist. I'm not going to have 4 in my hash map because it has a count of 0 anyway. So this is the dynamic programming solution. And now I'm going to code this up for you. Okay, so now I want to code this up, and I want to have a hash map like this. The initial hash map that we start with, we want the base case to be true because we want to say that we have at least one subset that has an OR value of 0. So we're going to initialize the hash map like this. This is our base case. This is going to allow the rest of the solution to work, and I'll point out the part where this is going to be important. So now I'm going to go through every number in nums. I want to create a copy of this hash map. So that's easy to do in Python. We can do new DP. This is the current row that we're populating. I'm going to create a deep copy using the built-in function. I think there are other ways to do this as well. I just don't know what they are off the top of my head. And then we're going to iterate over all values in that hash map. We're going to actually go through the key value pairs. So I'm going to use in dp.items in this hash map. And remember, what are the items? The key is the current OR, and the value in the hash map is the count of that current OR. How many occurrences of that OR do we have? So here I'm going to say current OR, comma, count in dp items. I want to use those to populate this new DP. And I want to use the current element. So basically I'm saying for this current element, go through all the subsets that we have and OR this with the current OR of those. So I'm going to do this. n ORed with current OR. So now this is the new OR. I could make a separate variable for this. I guess I will, just to make it easy. So this is the new OR. For the new OR, we want to update the count of it in new DP. So new DP of the new OR. Here, it's easy to make a mistake. So I'll actually try to slow down here and explain this part. We're not only going to be adding 1 to it, because my explanation earlier might have been a tad bit misleading. Imagine that we have a single subset with an OR of, let's say, 1. And then we have the element 3, and we want to OR that with 1. We can create a new subset of this, 1, 3. So in that case, we do add 1. Now imagine if we actually had 2 subsets with an OR of 1. So I guess just to make it clear, that would be like this. So from here, now we're actually going to end up with 2 subsets with an OR of this, because like this is going to be ORed with all of those. Now 1 has an OR of just 1, 1, 3 has an OR of 3, so we'd have 2 subsets. If we had, let's say, 4 subsets of this, we'd end up with 4 subsets of the new OR. So this is the new OR, and we're updating the count of that new OR. It's not going to be incremented by 1, it's going to be incremented by the count of the current OR, or the previous OR that we were looking at. So here, we're actually going to increment this by count, not by 1. I'm sorry that I didn't have time to explain that in the drawing explanation, but I think this video is becoming long enough as it is, and I wanted to cover that when we actually needed it here. Now, after we fully compute new DP here, we're going to assign DP to be new DP so that on the next iteration of the loop that we can kind of start the same cycle here. Now, when we finally are going to return out here, what exactly are we going to return? Well, DP of whatever the max OR happens to be. The only problem is we didn't compute it. We could have a separate loop up here to compute it, but since we're just going to iterate over all the nums anyway, we might as well do that here. So I'm going to have my max OR, declare it, and then within this loop, I will just go ahead and compute it at the same time, or here with n. Now there's one last issue. The way dictionaries work in Python, the way hash maps work, if I try to add to this, and suppose new OR here is a key that's not existing in DP, this is going to give me a key error. So the best way to avoid that is to change this to a default dictionary in Python. So like this. And if we do that, we can't really pass in any values. So I will just set the base case like this. 0 is equal to 1. To quickly dry run through this, imagine we have an array like this, 1, 2. First, I'm going to have 1. I'm going to iterate over that. I'm going to go through my DP items. It does have a single item where the OR is 0 and the count of that is 1. I'm going to compute the new OR, which is just going to be 1 ORed with 0. So that's going to be 1. I'm going to increment the count of that OR. So now we have 1 OR with 1. So the next time we're going to have 2, we're going to iterate over this. So just to visualize it, these are the subsets that we have. Then we're going to have 2. 2 is going to iterate over the subsets that we have. It's going to be ORed with both of them. And then we're going to end up with these subsets, just 2 itself and 2, 1. Among all of these, the max OR is 3, and we only have 1 occurrence of that OR, so that's what we're going to end up returning down there. Let me run this as well. Okay, there's actually a typo up here. It's default dict. Sorry about that. But now this solution is correct, and you can see that it is very efficient. Now, first of all, I want to say that this is difficult, so please don't feel bad if you don't understand it. But I also want you to know that this is like far better than what the Leetcode editorial has to offer. I'm not trying to brag here, but my God, is this so horribly explained. They use a constant 2 to the power of 17. They make no mention of why they're using that constant. It has to do with the fact that that's enough space to hold 2 times the max possible OR, but they make no mention of that. They are very inconsistent in their use of time and space complexity. Here they say the variable max, where that's the max possible OR, and up above, they use the max possible OR, and they call it something else. Like in this solution, they call it max OR value. I'm not sure why they're doing that. Since 2 to the power of 17 is proportional to the max possible OR value, I have no idea why they didn't use a variable for that and why they put a constant here. It's just such a bad, poorly organized editorial. This solution as well, I mean, I'll run it for you and then I'll explain to you why it's so inefficient. I'm going to first just copy and paste it, run it. They use the array method, which is fine, But because of that down here, it makes it so inefficient. They're iterating over the max OR value, which they're not necessarily computing up front, but still it's going to be computed as they go. So iterating over this loop, most of the time, the I value that they're getting from this loop is going to be associated with a DP position where the count of this is 0 anyway. So this loop is going to be useless most of the time for reasons I talked about earlier. And that's why the runtime of this is not very efficient. This is why I think these editorials are so bad for beginners, because you might look at a solution like this and think it's efficient and not recognize these subtle points. It's just so horrible. So I'm going to show you one more solution, and this one actually might be my favorite one. And if you're tired from watching this video, how do you think I feel recording it? But anyways, the time complexity of this solution is actually going to be n times 2 to the power of n. So it's actually not the most efficient solution. Remember, the first brute force solution we came up with was 2 to the power of n, but the space complexity is actually going to be constant. And you're probably wondering, how is that even possible? Well, this is a tricky solution, and I'm not even finna lie to you. I actually did not come up with this one myself. The idea is actually pretty simple though. If we have 4 elements and we want to go through every possible combination where we include an element or we skip an element, we can do that with a decision tree, but watch what I'm drawing for a second here. If we wanted to pick none of the elements, we could do something like this. If we wanted to pick the first element, skip the second element, pick the third element, and then skip the next one, we could do this. And then we could also include this one. So I'm putting 1s and 0s down here. Is that giving you a hint? Perhaps we can iterate over all integers, not from 0, because that would include the empty subset, and we don't really care about that. The OR of the empty subset is going to be 0, and that's not possible given that we're given a non-empty array where all values are positive. So we're going to start here. We're going to start at 1. That would mean this subset, just 5 by itself. And we're going to go all the way up until 2, which would be just this subset, and then 3, which would be this subset, and then 4, which would be just this subset. And we're going to go all the way up until 1, 1, 1, 1, which would be all the elements. So if we iterate from 4, 1 up until 2 to the power of n, which by the way, 2 to the power of n in this case is going to be this 1, 0, 0, 0, 0, and that's because this is 2 to the power of 0, this is 2 to the power of 1, so 2 to the power of 4 is going to be all the way over here. That's clearly not what we want though. That's a little bit too big, right? So really we want to go for 1 all the way up until 2 to the power of n minus 1. So if we do that, we will get a bit mask for every single subset. So this bit mask represents a individual subset. So for example, this might be the bit mask. That would mean include this and include this element. Now, for a given bit mask, we want to compute the OR of it. And then if the OR of it is equal to our max OR that we're going to compute up front, if that's the case, then we'll increment our result by 1. So very straightforward solution. The only clever part is the fact that we can use bit masks here. Now, how exactly do we get the OR of this? Well, we can just iterate over the entire length of the bit mask. So if we're at this position, we'll be at 0, 1, 2, etc. And then to extract the individual bit, we're going to say, I'm going to have 1. I'm going to bit shift it to the left by whatever the index is. So if we're at, let's say, index 2, I'm going to bit shift 1 to the left by 2. I'm going to end up with something like this, 1, 0, 0. I'm going to take this number and I'm going to AND it with the number here. That's going to get rid of everything from here and here, since all of these are 0 and everything over here is going to be 0. And we're going to only look here, ANDing them together, we get a 1 because this bit is actually set. If it was a 0, we would get a 0 in the output. So we're going to use that output, whether it's a 1 or a 0, as sort of a true or false. So you tell me, if it's true, what exactly are we going to do? That bit is set. Do you remember what that bit represents? That bit represents the number at this index. So since this is the ith bit, it's going to be associated with this number. Now, technically, the way I'm coding it, this is 2, so technically it should be associated with that one, and that's fine, actually. Like, this bit doesn't actually have to be associated with that number. We could do it in reverse, because it's still unique. I mean, this and this and this and this, it's fine. Just the fact that we have the bit mask in reverse order, that's not going to change anything. We're still going to generate all possible subsets. So if you want to make the index of this consistent with the index of that, it's perfectly fine. You can do that. It's going to be more work, so you don't have to do that. So this is pretty much the whole solution. It's constant space because we just have a single 16-bit integer in the worst case. And the reason we're able to actually do this solution, I should have mentioned this earlier, the bit mask only needs to be up to 16 bits because the length of the input is only going to be up to 16. Now, obviously, for an array of like size 100, you couldn't really get away with this solution. So it's not a very practical solution in most cases, but it's interesting enough. And this sort of pattern comes up in a lot of other problems. So I'm going to start with a bit of boilerplate where we compute the max/or up front. Next, I'm going to get the length of the array because that's going to tell us the size of the bit mask. And I'm going to have a variable result, which is going to count the number of subsets, and then we're going to return that. Now let's go through every possible subset. Do you remember how we're doing that? I'm going to call it subset. It's going to go from 1 all the way up until 2 to the power of n minus 1. So 2 to the power of the length of the input minus 1. These are all possible subsets, and this bit mask represents which elements we are choosing. So now we have a current OR to compute. Initially, it's 0, and then once we compute it, we're going to increment the result if the current OR is equal to the max OR. Otherwise, we're not going to increment it. And we can compute the current OR by going through every position in the subset, every relevant position. So mainly the length, like that tells us how many positions we have. So for, let's say, n in, or rather I'll just say digit, I guess, in range length. Actually, I is probably better because it represents the index, the position that we're at. Then I'm going to take my I and I'm going to shift it to the left, or rather I'm going to take 1 and shift it to the left by I. So this is the bit that we care about. And then I'm going to take this and I'm going to AND it with the current subset. So this will tell me if the bit in the subset is actually set or not. If it actually is set, then I can update the current OR. I can set the current OR to be ORed with the element at index I in the original num. So something like this, nums of I. Okay, a sloppy mistake by me. Remember in Python, the range function doesn't actually include the last value. So here, even though in the drawing explanation, I said we're going from 1 up until 2 to the power of length minus 1, that is technically correct, but in the code, we actually don't need the minus 1. It's kind of annoying when the code doesn't line up with the explanation, but that's mainly due to Python specific stuff in this case. If I had like a regular for loop and I was doing like less than or equal up until here, I would have done 2 to the power of length minus 1. Let me run this now. And as you can see, this one is actually not as efficient as a couple of the others, but the space is definitely more efficient. If you found this helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.